Right. Good morning, everyone. So welcome back to RoboCup at Home Education Online Classroom. And today is week number 6, and we will have robot navigation. Okay. Uh, for this class, we will do it in simulation. So you just need to prepare your laptop as usual and follow the class with me. Okay. So first thing, the arrangement for today. So as usual, we will divide into 2 sessions. For the first hour, we'll talk about the SLAM map building. And for the second session, we'll talk about the autonomous navigation. So both of this content will show you how to do robot navigation uh, that makes your robot able to move around your house autonomously. And today's content, which is the gazebo, the ROS gazebo simulator, but I can say are the same as compared to the real robot development because we just switch between real physical robot and the robot in the simulator. And also we can actually do the same process like build a map and then get the data from the virtual environment, which is mimic the real environment. And from there, we can instruct our robot to move to various locations in the virtual environment, which is similar to the actual environment. So this is basically the content for today. And yes, as usual, we will have a Facebook Live, so just be careful on your privacy. This video will be recorded and also will be published online. Okay, so let's start. Okay, so from last week assignment, so last week assignment we talked about how to combine the speech interaction, which is the speech synthesis and also the speech recognition, that you can make interaction with the machine or with your robots able to like interact using voice. Then we add this speech interaction module with the visual module that you learned like last week, how to track an object using color or how to do the face detection and so on, how to put these two together to create some interactive robot vision application. So for example, like when someone is actually coming near to your machine, so your system able to detect that person and do greetings or do some interactive chatting and so on, right? So that is the previous assignment, and today we will use this system, especially the speech part, to add in robot navigation. So you can actually instruct the robot to move to certain places, to go to certain room, to find someone, and so on. So you can combine the speech with the navigation, and also you can add on the visual perception later on. For example, like if you ask your robot to move to the living room and find a guest and so on. So first you use the speech to move the robot to certain place. Then the robot will autonomously from point A move to point B. Then from point B, it will use your vision system to find someone or the one that you have recognized or trained before in a database. So from there, a lot of application can be developed based on this architecture. Right. So with this prerequisite or the previous assignment that you have done, so let's see how we can combine with the mobile system that I'm going to introduce today. Okay. So first, what we need for today's lecture. So as usual, you can do this thing totally at home. So what you need for the hardware is just your laptop computer with the software that requires the Ubuntu background. The OS, right? Then on top run of ROS, and also today we will use a new tool, which is the Gazebo Simulator. Although I have used it before, but today we will use it more extensively because we are going to use the Gazebo Simulator to simulate the environment and also your physical robot. And for your physical robot, not just the mobile platform, we also simulate the sensor. So which means you have everything being simulated in a simulator. But what I can assure you is like your development or the code that you develop later on is about 90% similar to the one that you're going to put on the real robot. So when you have the actual turtlebot and actual Kinect sensor, so the whole code that you have developed can actually put into the real robot and give you very similar results, right? And some related component software, which is I'm going to that we are going to use for our mapping and also localization, path planning, and so on. Okay, so these are the things that you need for today. Right. Then I divided the content for today's class into this few subsection. So in the first SLAM map building, so before I can show you how the robot able to build the map or the SLAM, simultaneously localization and mapping, I need to clarify a few concepts. So I will start to introduce to you the mobile robot model. Then from there, I will introduce you how the audiometry and the localization for mobile robot works. So with that, only we able to understand like how the SLAM works, and I will show you a practical solution to actually build the map, right? Then for the second half, I'll show you how to use this map to do path planning. And with path planning, you can able to ask your robot to navigate autonomously from point A to point B. And while in the process, you also can do like object avoidance. Okay, so these are the content for today's class. Okay, so we start with mobile robot. So for mobile robot, actually we have various type of design in terms of the mobility, and also like we use various principles for this kind of mobility. The purpose is to make the robot able to move around. Okay, so we have many design in mechanical engineering. For example, I put out a few example in this slide, so you can see like the legged one, two-legged or multi-legged, wheel, track, and then for the wheel you can only have you can also have omnidirectional. For example, you're using the omnidirectional wheel that make your robot able to move in all direction. And also we can have mechanism very similar like animal, for example, crawling, for example, like snake, or even like wall climbing. So not just on the ground, but also maybe you can like make the robot to do wall climbing on a flat surface. It's like you know, the windows cleaning robot and so on. Then we also have hybrid system, the leg, the wheel that combine together, very similar like the one we designed for the Mars rover and so on. So you can see various different type of mechanism and so on. And why today I introduce this concept is because we need to understand a very fundamental concept called audiometry, which is how to actually estimate the distance travel by your robot. So we need to start from your robot model, how your robot actually move around. So we take a simple example that we are going to use for our robots, which is the wheelbase. Okay, so wheel mobile robot, the mechanism. So from here, for the wheel, I try to pick up a few common example in mobile robots, which is over here we have three main common one. So the first one is the most common one. I can say like maybe 80% of the mobile robots or any robots that we use for education and so on belongs to the first one, the parallel two wheel. So it's like you have two wheel differential drive that both controlled by different actuator, separate actuator, and that will give you a very flexible movement. Okay. Then the second one is the Ackermann steering, which is very similar to like your bicycle or your normal passenger car. Okay, which is you have a steering wheel in front that will steer the front wheel, and the back wheel will give you the movement of front and back. Then for the third type, we have the omnidirectional, which is you have something very similar to the first one, but in 3 set or 4 set. Okay, so from there, the robot able to move in all different directions. Okay, so for this concept, in mathematics, we try to explain in this form. For example, you can see from there we written the holonomic or non-holonomic design. So holonomic and non-holonomic design, the difference are for holonomic, which is the robot movement, okay, which is in 2D plane, you will have x, y, and theta. X, y, and theta means how to move in x direction, how to move in y direction, and how to move in different orientation. Okay, so for all this degree of freedom, if it can be controlled independently, which means it can move in x, y, and also theta independently, separately, then it is a holonomic design, which is most of the case, the car, our mobile robots, or your bicycle are not holonomic design. It actually belongs to non-holonomic design, which is the x, y, and theta cannot be controlled independently. Why? It's because like very easy explanation. For example, your car, when you do parallel parking, you're just not able to move sideways, right? So the sideways, for example, is your x. So your robot not able to move sideways directly, but it need to make a turning into sideways, right? So which means the parameters in terms of a sideways movement is not able to achieve with particular the first type and the second type. But for the omnidirectional type, it is actually a holonomic design, which is it can move in various directions independently. Right, so that is a very brief explanation about this mechanism. And why I spend time to explain to about this is because we need to know the model in order for us to calculate the audiometry. So what is the audiometry? So I take example of a parallel to wheel, okay, because that is actually the model that I use for the robot that we developed all this time, which is a robot base. And most of the floor cleaning robot is designed based on this mechanism. Okay, so we have two wheels that can control independently, and the wheel can turn like to the front and to the back. So clockwise and counterclockwise. So both when pointing in different directions. So it is actually I explain in the way that the wheel is turning forward or backward. Okay, right. So we have the left wheel and right wheel, which is the control parameter is the speed. So the speed for the left wheel and right wheel, and over here we are using the linear speed, which is the VL and VR, which is the speed going in front, which is not the turning speed of the wheel, but the speed to the front. But of course, we can actually easily calculate the speed, the linear speed from the rotation speed of the wheel. That one you can easily calculate. Then a few concepts that's important over here. For example, like the R, which is the turning radius. So for example, your bicycle or your car, you need to have certain turning radius, right, due to the Ackermann steering design. But for mobile robots, using parallel to wheel, we can actually have zero turning radius. It's because like when both wheels, one go in front and one go behind, the whole robot is actually performing a point turn. A point turn means you are turning on the same point. Okay, so that is a point turn. Then we have the design parameters of the wheel track. So how far is the distance between the two wheels? So these are a few parameters that we are concerned when designing your parallel to wheel robot, especially when we want to like estimate the audiometry, which is estimate the distance travel from according to the time travel, right? Then we have another concept, which is the K, the curvature. The curvature is actually the 1 over the radius. Okay, right? Yeah, but this is just a few very common concept. Okay, so with that few parameters definition, we can derive the speed. And important thing in this slide is like we want to find the control parameter and the output parameter. Okay, which is you can see in equation 8 and 9. So we can have the V and omega of the total robot, which is the speed and also the turning or the rotation of the robots with respect to the left and right speed. So that's what we want, because the left and right wheel speed is our input. Okay, so that is something we can control. We can control the motor, and we can control this parameter. Right, and the output that we want is how the movement of the robot, which is the overall speed and also the overall rotational speed of the robots. So we have the V and also the omega. Okay, so this is the model that we need in order to do the calculation later on. Right, I go a bit faster for this because like I think this theories you can actually find a lot more detailed explanation on the web. So important thing is how we get this audiometry in order to explain to you what is audiometry. So audiometry is the x, y, and theta value of the robot as time go on. So for example, like we have certain input of VL and VR. Okay, so that is something that you can record down, right? So that is something that you input to the robots and you can record over the time, the value. So with this value, can we calculate like what is the robot position after a certain time? For example, after 1 second or after 5 seconds, after 10 seconds, and so on. So how to calculate that? Basically, if we put out the equation, will be similar like equation in number 10, right? So which is if we plot the x and y, okay. So if we plot the graph of t versus the distance travel, okay. So we can have the curve that represent the area under the curve that represent the distance that's traveled by the robot. So which means if we can find the integration of the equation in number 10, okay, so which is the V over the time and also the omega over the time, so we can find how far the X, the Y, and the theta, right? So that is the basic concept, right? And in order for us to solve this equation, if curve varies as your input varies, right? And it is very hard to like, for every instant, you're going to like solve the equation, okay? So normally what we do is like, we will do numerical way to solve, which is to find the area under the curve, right? In order to find the area under the curve, we divide into a very small strip, okay, to fill in the curve. And then we have the strip models, we have the trapezoid models, and so on. So various numerical methods can help you to find the area under the curve, right? So that one we can find the solution using the numerical way and let the computer to calculate. So that is how we formulate the strategy to estimate the odometry of the robot using computer. Right, so next slide. Oops, this is the first one. Okay, so now you understand how we can estimate the odometry. So now let me explain in a total robot way. Okay, so now imagine the whole robot is moving on the plane. Okay, so now we have the robot that's moving over the time. We have, okay, so over here we have the base link, which is represent the robot base, and also we have the odom, which is represent the odometry. So over here the definition is like, the odometry is the use of data from moving sensor to estimate change in position over time, right? And odometry is used by some robots, whether legged or wheel, to estimate, it's not determined, it's to estimate their position relative to a starting location. So you always need a starting location, and then you calculate like how the robot travel based on the wheel, the speed, and also the time. Okay, so that is odometry. So that is the definition. So in Turabot or in our system, how we actually obtain all this value. So just now we talked about, okay, we know the control value, which is the V, L, and VR, but in real robot, how we actually get that? Okay, so over here, we have two sets of data. So the first step comes from, of course, the encoder, right? So we can put an encoder on the wheel, then we can calculate the rotational speed, and from there we can do we can use the kinematic model and calculate the VL and VR. Okay, so that one is quite straightforward. But we can also have another set of data coming from the gyro. So if you know gyro, it's very similar like the sensors that in your mobile phone to track the acceleration in all different directions. Okay, so why this acceleration value is important is because this value will give you, for example, so from the acceleration, you can integrate and you can get speed, and you can integrate further and you get distance. So it's very similar like just now what we calculate for the distance travel. Okay, so the gyro will give you another set of distance travel by your robots. So we put these two together. So you can see over here we have two sets, which is one come from IMU, which is your gyro, and another one is from your odom, which is the odometry, which is calculated from the wheel. So using these two set of data, we use the extended Kalman filter, right? So if you're interested in Kalman filter, it is a very widely used filter in mobile robots for the time series data analysis, right? So it is used to combine these two data to find the differences and then to give you accurate estimation of the odometry, right? So with these two set of data, we will get the odometry. I'm not going to explain in detail like how this Kalman filter works. You can find on the web like how this thing works. Okay, so but over here the idea is like we use the odometry data from the wheel and also the odometry and also the data from the IMU, which is gyro, and combine and get an accurate estimation of the odometry of the robot. Okay, right. So that is the concept of odometry in the robot. So below is some explanation on the Kalman filter. So the EKF into the robot that we use is called the extended Kalman filter. So this is one tool that is running in our code in order to find a good estimation about the current location of the robots. So because we know that over the time we have a lot of noise, like for example, your wheels will slip, your sensor data might be not 2D but 3D, so it will go in different directions, so it will give you some inaccuracy and so on. So Kalman filter is good in this case that try to help you to identify all the noises and give you a true accurate value that is close to the true value. Okay, so done with the audiometry concept. So now you know audiometry, you know how we can estimate the distance traveled by the robots over the time. Okay, so the next concept that you need to know is the localization. Okay, so what is localization? Localization is like, for example, we have a living room, especially in the pictures on the right hand side. Okay, so for example, that is a living room, and you have a few sofa with a tea table, with a coffee table in front, and then we have a robot that's moving in this environment. So if we take a slice in a 2D plane, so you look from the top, you can get something like on the right hand side, sorry, left hand side. Okay, which is, you can see the black boxes represent the big one represent the sofa, and then the small 4 dot represent the leg of the table, coffee table. Why? It's because like when we do the scanning, okay, we only do in one plane. Okay, so and you imagine like the height of the sensor is over here, so it actually see through this plane. Okay, so for example, like you cut through this plane and then you see the cross section. So this is the cross section that you get. So the table will become 4 dots, because these are the 4 dots that appear in the map that we are going to build. Okay, the map is, we are going to get the map something very similar like this. So based on this value or this map, okay, this is a 2D occupancy map, I can say. The black represents the region that the robot cannot enter. It's not a free space. But the white one is a free space, which means the robot can enter the white color area. Okay, so the black and the white color area. Okay, so localization is we try to use this map and also the current scanning of the environment and try to find the current location of the robots. Okay, so how to do that? Okay, so so just now I mentioned about this. So in Turtlebot we have the system that give you the auto combine, the Audiometry. Okay, then we have another set of system which is we're using the RGBD sensor to give you another estimation for your localization. Okay, so for example, over here we have the Kinect sensor. So, okay, so this OpenNI is the driver for this Kinect sensor. It's going to give you the data for the 2D scan, right? The scanning that just now I said, right? So based on the sensor data and also the driver, OpenNI driver, so on. And then you can see like we have something called the point cloud to laser scan. So the laser scan came from all the in one plane from all the direction. Okay, and we will input this data into software tools that we use in our localization. So this tool, what we do, okay, AMCL means adaptive Monte Carlo localization. So this tool, what it do is like it takes the input from the scan, and then it takes the input from the map and also the TF. The TF means the current okay, it's a transformation. If I'm not mistaken, should be the transformation function of the robots, but you can regard as the current data of the robots, which is like, for example, the current location with respect to the map and so on, X, Y, Z. Okay, so we have the up from the scan, which is the sensors from the robots. So we have these three, right? So with these three data, the AMCL will try to tell you the localization estimation. Okay, so it will try. And if you want to understand how AMCL works, okay, that is another big system. You can find out more information from the web. But I will tell you a simple concept after this. Okay, right. So AMCL. So AMCL stands for Adaptive Monte Carlo Localization. It will try to figure out where the robot, okay, will need to be on the map in order for its laser scan to make sense. So which means you want the laser scan match with the possible location in the map that match with the location in the map. Okay, so for example, in any point of the map, okay, when your robot stand there, you can actually estimate what will be the laser scan based on the map, right? So that is the map information, and also that can give you the possible laser scan data. Okay, then you have the real data from your laser scan. So you are comparing these two data. Okay, so when comparing these two data, of course you can have a lot of possibility, right? In a map, you can have different location and different orientation, and will give you laser scan data that is matching with the data from the map. Okay, so from there, we use a lot of computing power to do this. So we put point that is possible for the robots to be there. Okay, based on the current laser scan, and AMCL figure out a way that you try to move the robot to the next step and try to calculate again the estimation. Okay, so as your robot moving forward and forward, so the estimation change from the first one to the second one and third one. And then for the particle which is for all the possibility, you try to reduce the possible thing after changing the location. Okay, so for example, if your robot is in and looking forward, so if in the first second you can see this, but in the second second, I mean like the next second, it cannot see this. So based on these changes, you can actually reduce the possibility, the possibility, which is the point, the particle that previously you estimate. So when this process keep on continue, eventually you will only find the last possibility that can match with all the sensors, all the data throughout the whole course. So that is how we can finally estimate the location, right? Okay, so I'm not going deep into this, okay, because it's a long story to explain the whole thing. So the idea of this adaptive multi-color localization is it tries to find a possible location based on the sensor data and also the map. And then as the robot moves, it tries to eliminate the case or the changes that not true for certain estimation. Then you try to reduce this until finally you obtain the possible location that matches all the sensor data, right? And that is the most possible location of the robot. Right. So okay. So now let me show you how to do the mapping in practice, okay, and localization in practice. So how to do it? So you're going to look at this wiki tutorial on the ROS wiki, but okay, of course you can see it later. I'm going to like in brief tell you the steps and you can run it. But of course, if you want additional information about the steps, you can read from here. And also the tool that we use is this OpenSlab Gmapping. Okay, so the Gmapping is the tools that we use to do the official site and also go to the REST wiki site to understand about Gmapping. Okay, so these are the information you can read later on that I will skip in this lecture and tell you straight how to do it. Okay, so how to do it? All right, so how to do it? Let's start with, let me start my TeamViewer. Okay, so give me a second. So I need to connect to my robots. I need to put this thing down. Okay. Okay, and where am I? Okay, this one. Right, so before we can the simulation, we need to, before we can do the navigation, we need to have a platform, right, to do it, a robot platform. And over here, I'm using the simulator is because like we don't have the real robots. Okay, but, why this is not okay? Try to. Okay, so we have. I need a bigger view. So okay, so just try with this setting. Okay, so we use this gazebo simulator to simulate the environment and also the robot and also the sensor. Okay, these are the three things that we need. Okay, the robot means the wheelbase. Okay, to give the movement for the robots, the sensor to give you the laser scan, and also the environment for the robot to move around, right, to interact with the environment. So in order to have this infrastructure, so it's either you have the real robot or over here we use the gazebo, which is simulator. So we need to bring up first. Okay, so always we need to bring up. First is like if you haven't installed, okay, you can install, but by default, if you install Turtlebot software package, you should have this installed. Okay, but you can hit to the Turtlebot simulator, which is the gazebo. You go to the wiki page. Unfortunately, it still stay on Intego version, but yeah, I have tried everything and it works under Kinetic. Okay, so you can even have this simulator in here. So over here, let me try to bring up this thing. Okay, so ROS launch. Turtlebot Gazebo. So we are using the Turtlebot Gazebo package, which is the package that the Turtlebot community developed for use to use the Turtlebot in Gazebo, right? Then the third option is the launch. We are going to use the launch build environment. The wall means the simulation environment in Gazebo that we also put in the Turtlebot model. Okay, so this is a pre-made environment with the robots, everything, the infrastructure that you need for today's development. But of course, we can have a separate, we will have a separate class based on Gazebo to show you how to build the wall, how to build the environment, how to put in the Turtlebot model and so on. But that will be another class. So today we are going to use the pre-made environment for us to study and develop for navigation. Okay, so we're going to use this. So once you run this, it might take some time for the first time for you to launch this, but after the first time, which you were okay, so this is a simulated world. So we have this environment. So I can turn around and show you the furniture. Okay. Okay. So this one may be a bit lagging, is because like it requires. I also need to get used to use. So you can see. Okay. So this is our robot. So we have a wall, and we have a cylinder and a box, which represents some obstacle. Okay. So we can have various kind of furniture environment, but okay, it works the same concept. So today, what are we going to do is we are going to use it here, but okay, this is okay. So we can see the sensor. It's over here because we defined the Astra sensor, so it is Astra sensor. Okay, but it works the same in this environment. So I'm going to show you like okay. So for the first half, how to use this robot and the sensor to this environment. Okay, right. So let's start. Okay, you need to keep this environment and keep it running. Okay, then we're going to need another terminal. Okay, so after you have the work, so first is like we need to run the G mapping. Okay, G mapping. Under this gazebo package, we have the G mapping demo. Okay, okay, we run the G mapping demo. Okay, so we run it. Okay, now package. Okay, and everything looks fine. Don't have any red color. You can't see anything over here because we are generalization because you want to get the map. So you want to see the sensor data and how with the map. Okay, so we are going to use the RVs. Okay, it's a bit lag. It's quite heavy this operation, so you need to have some patience. Okay, so we are. So actually, other than this GMAP, the command from Gazebo, the rest of these are very similar to the actual course launch trigger board RVs launcher, then view launch. Okay. Okay, then we have the RVs. Okay, but over here, modification in terms of some our GMapping. Okay, so over here we need to change in the local map. For the course map, we need to change this term. Will take the data from the actual robots. Okay, in the end, we try to not to say fact, but fabricate this data in RVs. So we are going to first step. So course map. So we can see this warning, which is change this into the map. So we can see map is available, right? So then I start to get data. Okay, but this is still you don't see it by default, but it is also a warning that you need to change. Okay, so. All right, so with that, for your G-mapping tool. Okay, so everything looks fine now. Okay, then the next thing is okay. So you are going. So in order to do the scanning, you need to move the robots around. So in order to move the tele out, which is our remote control tools. Okay, okay, you can see like my task is using a lot of resources. So you need to be very patient when you want to do the fast computer. Then yeah, the performance will be better. Right, so we run the tele out, and then we are using the keyboard. How to use this keyboard tele operation is very simple, and this work on the real robot. So the middle of your keyboard, I represent to move forward. Okay, this comma represent to move backward. J and L is not omnifunctional. Okay, so this is to control the left right wheel to give you the differential. And O is actually having different. For example, like U is actually the left and right wheel going forward, but faster speed than the left wheel. So you can see it is actually turning towards left side. And K is actually to stop, but it doesn't matter because you're not running too fast. Please keep your speed slow, active, or else your keyboard operation is not going to effective. Okay, let me rearrange. I need some space. I will rearrange. Oh, it's very environment to show you. Okay, I need to this one down a bit. Make this smaller. Okay, maybe you need a bigger display for this. I'm going to force have a smaller one. I'm not going to scan the whole thing. So in here, okay, so for example here and this over here, this. Okay, you need this in order for a bit bigger. So I'm going to move my keyboard for the robot to move. It's going to catch to record all the. I'm going to move my robot. So let's move front. Is updating, and when the laser scan hit the wall, like this arc represent this thing. This line is this thing or this whole operation until you get the whole map. Okay, you slowly scan some more. You can see. Okay, right. So this is how you do through this, and you need to move very slowly. Okay, in order for this scan to come out with all this data in your map. Okay, so I'm not going to. You just need to move your robot around. If the robot cannot scan nicely, you can scan again and again until it gets the figure. Okay, that you can see. So try to imagine like data. Okay, so all the boundary. Once I have this, I'm going to save the data. Okay, okay. The map saving. You can always I put the home directory, which is the easiest path for you to find your map. But of course, so for example, right, never mind. I can remember. Okay, I can remember like it's a raw map server, map saver. Then okay, this is where you the location that you want to save your map. So my map. So just for the save, I add my map 2, for example. Okay, but you can change to any name you like. Okay, so I do this and make sure you get something like done, which means you have. And just to double check, you can go to I have a map. And now this time I have this, and you can see the PGM and what is the YML. So for the YML, is it going to run? Okay. So YAML is just a metadata. For example, like the meta file actually tells us where the image, which is you are going to move the file of your map. Please don't forget L and the PGM have to come exact. You need here the full path to your image. So just in case when you move to other places, if you don't update this PGM file, okay. And for the PGM file, it is just is similar to just how the map it is actually an image. You can do post-processing to act, for example, like just now you remember the four leg of the table, imaging tools or imaging software to combine that 4 dot into a full table, okay, by putting black on it. And any place that's supposed to be white, then you just paint it really enhance, or how to say big noisy and it's not perfect and so on. You can use the imaging software to do some correction on your map. Maybe not going to work well with some tools like going to work, I think. But for the Linux environment, yeah, it is. Some of my students, they use Gym to this intro. Okay, so with that, I have done for the first session of this. So we are going to take a break. So now it's 10:53. So we'll start the session again by 11. Okay, we'll start the second session by 11.